guys, welcome to part 2 in which we learn about Lenz's law, or what's with the negative sign, Mike? Referring, of course, to Michael Faraday, in case you did not know that was his first name. All right, now, the negative sign may have been a point of confusion in the previous video. Maybe you were concerned that I didn't talk about it. Just don't mention the negative sign. All right, but now we need to talk about it and why it's there. So Lenz's law says, more or less, that whatever the change in the flux of the system may be, the system will act to oppose that change. All right, you should write something like that down. Whatever the change in the flux is, the system will produce a current, or, well, an EMF that will make a current that will oppose whatever that change is. So if the flux is decreasing, the system is going to produce a current, which is going to make a magnetic field, which opposes that decrease in flux. If the flux is increasing, then the opposite is true. So whatever is being done to the system is going to respond in a way that attempts, anyway, to counteract that change. All right, so two things to look at here. One would be, I know we already did this demo, but I want you to notice something that I maybe didn't mention last time, or that you may have forgotten. The needle moves one way when I turn the current on, and the other way when I turn it off. It also does a lot of bouncing around because it's on a spring, but if you look at the initial direction of motion, right, it goes one way and then the other, and that direction has to do with Lenz's law. Why is the current going that way? All right, so I'm going to make an animation that goes along with this so you can get a little bit of a better visual grasp for what's going on. But here is at least a sketch which is going to attempt to show that. Suppose that we have a loop of wire. All right, and the magnetic field inside of it is out of the page. You know, you can't see that too well in the video. Let's make it be going, how about into the page? So we'll draw X's instead. Sounds good to me. All right, so the magnetic field is going into the page. Well, if there's just a magnetic field and it's neither increasing nor decreasing, nothing happens. We just have a loop with a magnetic field going through it. Where's the magnetic field coming from, Mr. Errico? I don't know, some other object that's nearby. It doesn't matter for what we're doing right now. There just is a magnetic field from some other source. All right, now let's suppose that that magnetic field is decreasing over time. So they might, you know, if they're giving you a question on this, do something like, yeah, the magnetic field equals like this function. All right, and so thus we're going to say decreasing over time because it says B naught, that would be an initial value, minus KT. So whatever it is, it's going down, right? All right, fine. It's decreasing over time. There will be an EMF induced since the flux is changing. All right, but then the question would be, does that EMF push current clockwise or counterclockwise? And if you like, you can even actually draw in the induced EMF like there's really a battery. Ooh. Right, there we go. All right, so does it point this way or the other way? Which one is it? All right, now the answer does not so much depend on whether these are X's or dots or whatever, or exactly whether it's the current, the field is increasing or decreasing. It depends on actually both of those things. All right, remember the goal here, the goal of the system is to oppose whatever the change is, which is happening to the system. So if we have a magnetic field which is into the page, but decreasing in magnitude, that means that the flux in the into the page direction is decreasing. Therefore, the system will attempt to oppose that change by having a current that makes a field in that same direction. All right, so let's walk that logical process through again. If the field is into the page, but it is decreasing in magnitude, the current that will be induced in the loop is going to attempt to make a field that's into the page in order to oppose the decrease in the field. All right, or rather, decrease in the flux. Okay. All right, so that means, based on my second right-hand rule, that the current will go in the clockwise direction. So like that. All right, the answer for whether the current goes clockwise or counterclockwise depends on, we said, whether these are dots, x's, and whether the field is increasing or decreasing. So let's take as a different example now. Oh my gosh, I changed it to a plus sign. What will happen? All right, well, you could probably guess what's going to happen. The answer is going to be the exact opposite. Okay, but the reasoning process would follow those same lines. If I say the field is into the page and the field is increasing into the page, the loop is going to experience an EMF that will make a current that will oppose that increase. That means it's going to try to make a field that goes out of the page to oppose the increase in flux into the page. Therefore, according to my second right-hand rule, the current would need to go counterclockwise. So if I had a different function there, right, a plus instead of a minus, the EMF goes the other way. All right, let me switch it up here. Oh my goodness, they are going to be dots now. And I've learned my lesson. They're going to be nice and big so you can see them all over the internet, like from space just about. All right, so now we have a field in this new case that is coming out of the page towards you. All right, if that field is increasing in this direction, the current in the loop is going to try to oppose that increase in field towards you. That means that it's going to try to make a field that goes the other way, right? Drag things back down to normal, right? It's fighting this change. It's fighting the increase in field in that direction by making a field that goes the other way. So if these are dots coming out towards you and the field is increasing, the current in the loop will make a field into the page, and therefore that would involve a clockwise current. All right, now I can go through all the various possibilities here, but ultimately it boils down to you got to understand that what the system is trying to do is keep the flux constant, okay? So it doesn't matter what the flux is at a particular moment. What matters is the change and how it's going to undo or attempt to undo that change. All right, now let's talk about one other really important scenario with this, which is motional EMF. Let's get rid of that. Because motional EMF looks a little bit different and also allows us to talk about some other important observations relating to Lenz's law. All right, so there's our bar that's going to slide down the contacts. I guess I'll put dots. There we go. All right, so as this bar falls, which it will fall because gravity will pull it down, the flux is increasing. Why is the flux increasing, Mr. Errico? The magnetic field's not changed. We covered that in the last video, if you recall. The area is increasing as this thing falls, right? We would not talk about the flux through the bottom part here unless this were closed off, right? If this was a complete loop of wire down here, then we'd have to talk about the increasing flux through the top part and the decreasing flux through the bottom part. All right, well, the bottom is open here, so we don't have to worry about that particular wrinkle. All right, but the flux through the top is going to increase as this falls. What will this do? All right, we have a flux out of the page. That flux is increasing, not because the field is changing, but because the area is increasing, okay? So out of the page flux, therefore, since that flux is increasing, the current in the loop is going to attempt to oppose that increase out of the page by making a field into the page. Second right-hand rule, that means we're going to have a current to the left through this bar, right? So clockwise all around it. No, you'll only get another color here. Okay, so there's our current, right? Going through that. And the EMF that's going to produce will be negative BLV, where L is this distance here. Okay, now here's a fascinating phenomenon with the falling bar problem. Since there's a current flowing through the bar, and that bar is in a magnetic field, there will be a magnetic force on the bar according to this equation that we learned last unit, right? The force on it is ILB. That's not very visible. Let me try again. All right, the force is ILB. So as this thing falls, it's going to have a current, we said, in the clockwise direction. All right, therefore, through the bar, that would mean a current to the left. If I use my first right-hand rule now, right, I would say current, field's out of the page, so I got to rotate my hand. The force due to the magnetic field on that bar will be in the upwards direction. Please note, it's opposing gravity. That goes right along with the whole theme of Lenz's law. Lenz's law is saying, because of this negative sign, that the system is trying to oppose the change that's being forced upon it. In this case, the thing that's making the change happen is that the bar is moving downward. So it stands to reason that the force due to this induced current would have to be in the upwards direction because it's trying to oppose the change. All right. This is all very academic. Let me make it very visible for you using the racing rings. I did not invent that name. Some genius in marketing did. So here goes. Plastic, copper, aluminum. I know it doesn't look like quite the same setup, but it's going to be the same basic thing. This is a ring magnet. So it's a magnet, okay? Picks things up, or at least iron things. Plastic, of course, is not a conductor, so if I drop it on that, it just falls normally, right? On the other hand, copper and aluminum are both conductors. They're also not magnetic, so this won't stick to the copper, it won't stick to the aluminum. But if this is falling, let's do that one more time. All right, as this is falling, what's happening to a particular cross-section of it is the flux through that section is increasing as this thing approaches that particular cross-section, right? So as the magnet falls, the flux through every section below it is increasing. It's also true that the flux through every segment above it is decreasing, okay? But the eddy currents, which are going to go either this way or that way, right, in that cross-section, are going to attempt to oppose the change in flux, which means exerting an upwards force on the ring. That's the only way that you could oppose the change. So as long as it's falling, that force will continue to push upwards on it. Aluminum is faster. All right, well, if you're familiar with these two metals, you ought to know that aluminum is not as good of a conductor as copper is. Where does that come in? Well, okay, let's look at this and look at this. The force depends upon not the volts, but the current. And y'all ought to know Ohm's law. Ohm's law. All right, there's our EMF. Current is EMF over the resistance. Okay, here's my EMF. We got BLV. All right, therefore that's the current, BLV over R. The force equation was this, therefore the force on that bar as it falls would be, all right, you got to put these two together. The little l and the big L represent the same quantity, right? That is the length of the conductor. All right, put those two together and we're going to get B squared L squared V over R. So at any particular moment, the magnetic force on it is given by that right there. All right, now there's a calculus problem to be done here, and I will probably work that out in a separate video. If what you're interested in is the terminal velocity, at terminal velocity, these two forces would be equal to each other. So if this is terminal velocity, I can set that equal to mg, and I discover that the terminal velocity is directly proportional to the resistance. All right, that should actually make sense because physically speaking, right, if you have a larger resistance, then you will have a smaller current. If you've got a smaller current, then the magnetic force will not be as great, and therefore it will have to fall faster in order to get the same amount of force to oppose the weight of the object. Okay, so lower resistance means ultimately it's going to have a greater current, therefore a greater magnetic force, and fall more slowly. All right, one more time, just because it's so fun. I could do this all day. Yeah, I think that'll be the next like 13 minutes of the video is just me doing this. Okay, just kidding. All right, thanks for watching.